that it's working. Preparing to live stream the meeting. Let's see if it works. This meeting is now live streaming on YouTube. Got it. All right. Good morning.
Awesome.
Yes, good morning, everyone. Thanks for joining us here on this Sunday as we have the Ellie in Space channel. I'm your host, Ellie, and I'm joined by astronomer and Harvard astrophysicist Jonathan McDowell. And I'll cut the anchoring voice. I'm in anchoring mode because I anchored this morning here in Salt Lake City. So, but yeah, exciting to have you here, Jonathan. How are you feeling today?
Relieved compared to how I was feeling a week ago. The deployments on Webb have been going just ludicrously smoothly, and it's just a testament to the team. So yeah, I think the whole astronomical community we're not there yet, but we're starting to excel.
I was going to say, I know that we have, another 5 months or so to really know if it's completely successful, but would you say like this was the hardest milestone yet, like in terms of difficulty?
We've brought down a lot of the risk now. The thing, there are still plenty of things that could go wrong, but the bits that we've done in the past week, unfolding the sunshade, unfolding the mirrors, were the most obvious, really, really tricky things that hadn't really been done before, and where it wasn't clear whether it was going to work. So I think and we'll talk a bit about what still could go wrong.
Right.
Not to be pessimistic, but yeah, it's a really good feeling that all of that part worked well.
Right. And I know that, we've talked about Webb a couple times before it even launched, and so there was a lot of, nervousness from you and just the entire space community as a whole. So, and you were telling me you shared like an artifact in one of my previous videos of a book, right? Tell people maybe about, because you've been following like the concept.
Yeah. So there was this meeting we went to in 1989 going, we're about to launch the Hubble, but what are we going to do after Hubble? And so that's how long it takes to do a project like this. And it was it's taken form over the years, and it's had a very rocky road of development. I think that's fair to say. It was underscoped. It was it was a very difficult project to try and do, and they tried to do it with too few resources to start with, because they knew if they asked for all the money they wouldn't get it, and so that delayed it. It was originally, they thought it was going to go up in 2013 or something, so it's only about a decade late and $8 billion over budget or something like that. But it's an amazing machine, and it's going to do great science. And so it is the biggest space telescope so far, and it's a whole new approach, and really, really ambitious project. To see it all come together is amazing. And so it's out there. It's now about 1 million kilometers from the Earth, so 600,000 miles, and it's trying to get to about 1.5 billion kilometers, where it gets to this magic Sun-Earth Lagrange 2 point 1 million miles towards midnight.
So you tweeted yesterday that you felt surprisingly emotional. I want you to take me through that moment.
Right. So the final step in the deployments was, it has this big 6.5 meter diameter mirror that's made up of these hexagonal segments, right? And because there isn't a rocket with a big enough nose fairing to fit that in, they had to fold it up for launch. And so it unfolded, and we could see, we can't see what's going on out there at L2. There's no camera watching it, but there's telemetry from the spacecraft that have the whole thing, right, is full. It's like bugged, right? It's full of temperature sensors and strain sensors that say how much various hinges are pulling on things, and motion sensors and stuff. And so you can reconstruct from that data exactly what configuration the telescope is currently in. You can see if something is sticking or something is, how far it is open. And so they tied that to an animation that, even though it was an animation, it was driven by live data from the spacecraft. And so you could see really what the spacecraft was doing. Sort of like mocap in Hollywood movies these days, right? And so we saw that last side flange of the folded up telescope fold out into this nice flower petal configuration that we've seen in plans for decades. And it finally suddenly it went from looking like a packed thing to looking like a telescope,
right?
And it just sort of clicked in place and went, oh, it's there, it's actually happened. We have a telescope. We have something that has a primary mirror to reflect the light from deep space sticking out in front of it, a secondary mirror that light bounces on and then back through the middle of the primary to the cameras. And so, yeah, it looks like a telescope now, and it's really there. And so that's amazing. Now, what's the trick is, right, it has these, I don't remember, is it 18 or something, hexagonal segments?
Yep.
Right? And each of them on the back has little actuators that can move them to sort of sync up. And so now if you took a picture with Webb right now, it's like you have like 18 different telescopes and you'd have 18 different images.
Wow.
And blurry ones at that, because the distance of the segments from the secondary mirror is what affects the focus. And so you'd have like 18 different, it'd be like a fly's eye kind of view of the world, where everything you were seeing not just double, but like 18-fold and blurry. So it would be really disappointing. And so the trick now is to ever so gently adjust the angles of each of these segments until those images go right on top of one another and sharpen up,
right,
to one sharp image. And so that's the trick that they have to do next. That's going to take them several weeks to get right. And so then you'll actually get proper focused images. So that's a really, that's not as dramatic visually as unfolding a big thing, but it's also very technical. I mean, you've got to sync this up to within the wavelength of light, which is a tiny fraction of a millimeter, right?
Wow.
And so it's got to be just right. So you're moving these big mirrors by tiny amounts, and it's such a precise thing to have to do. And then meanwhile, on the back end of the mirror hang off the 4 cameras, and those 4 cameras have to get cooler than they are now. So the sunshade is deployed, so it's in the earth light and the sunlight are hitting the sunshade and bouncing off, and on the dark side of the spacecraft, it's getting cold. And
like how cold?
Well, so 3 of the 4 cameras are going to get down to 40 degrees above absolute zero. And 40 degrees above absolute zero is minus 230 degrees centigrade, which is minus, I don't know, some 100 degrees Fahrenheit. I don't speak Fahrenheit, but
I thought it was cold here in Utah.
Right, exactly. It's insanely cold, but that's just the 3 near infrared cameras, and we have to get the 4th camera even colder.
How do they do that?
So, and the way they do that is they have a thing called a cryo cooler, which is basically a refrigerator. they have a refrigerator acting on the back of the spacecraft, and a big radiator to radiate away the heat.
Wow.
And that's going to get it down to, I believe, 7 degrees above absolute zero. So minus 260 something centigrade. And and so that's a really tricky thing to do. Previous spacecraft that have needed very, very cold temperatures like that have used liquid helium as kind of like a thermos bottle. And that has a disadvantage, which is that over time the liquid helium boils away. And so your mission has to end, right? And this one, it has some liquid helium in it, but as it's a sort of different design where it doesn't leak away, and it's more an active refrigerator. It uses electricity to power the cooler in a much more refrigerator kind of way, and that is expected to last for many, many years. And so this is going to be the first really long-term cryogenic, almost absolute zero mission. And so just again, that's got to work.
Yeah.
Right. And to get the mid-infrared instrument working. And the reason why these cameras have to be so cold, right, is that the wavelengths of light that Webb is looking at are in the infrared. And in the infrared, if we put an infrared filter on this Zoom session, you would be, I mean, you're already glowing in the but even I would be glowing bright in the infrared, right?
Right.
The everything gives out infrared light, and the warmer it is, the more infrared light it gives out.
Okay.
Right. So we're like, a bunch of 100-watt light bulbs in the infrared. We're super bright. And so if you just have a camera at room temperature, right, the camera is glowing bright in the infrared. Right. And so if you try and take a picture it's sort of like, having, if people remember film, right, if you have the film out in the light, it overexposes. And
you guys remember film?
Yeah, probably most of the audience weren't even born before the cameras. But you can't take a picture of something when the thing you're taking a picture with is glowing brighter than the thing you're trying to image.
Right.
And so by cooling the cameras, we make them dimmer. We're basically switching the lights off. And having a nice dark room to take the picture in.
Right.
And the more into the infrared you go, the beyond the visible, in the near infrared, it's okay to have it at 40 Kelvin, but in the mid infrared, where the MIRI camera works, you have to get it even colder, right? The further you go, the cooler the camera has to be. And so that's why this mid-infrared camera has to be even colder, has to be down at just a few degrees above absolute zero.
And I wanted to talk about the size, because I know that you were most concerned about the sun shield, correct?
That was particularly scary, yeah. And so you had this enormous 30-meter across
like size of a tennis court, right?
So they tell me, yeah, as I was telling you, I mean, I don't do sports. So for me, I only know how big a tennis court is by comparing it to the size of a James Webb Telescope. But yeah, it's big. It's big. It's
crazy.
It's certainly it's like much bigger than my apartment that I'm sitting in.
Yeah.
And so that had to unfold and stretch, and then it had lots of little motors around the edge of it to tug on it, to tension it, but not so hard that you rip it. And you had 5 layers that you had to also separate. They were packed together, like, folded like a parachute, I guess, or something. And you had to separate them out and hope they didn't stick to each other. In the early days of the space program, we had all kinds of problems with stuff doing what's called cold welding, where if you have stuff in the cold and the vacuum of space, it sticks together in a way that it wouldn't on Earth. Just like, I don't know if you've ever been in a situation where parts of you have it's been so cold. I'll tell you a story. I was observing on our little telescope. Just remember this 100-year-old little refractor telescope at Harvard, and I was observing with it on a very cold winter night. And my eyelid actually froze to the eyepiece.
Oh no!
I had to peel it off ever so carefully.
Oh,
Because when you get it cold, you can, things can stick. And
oh,
so yeah, so that's what we didn't want to happen. That was not a great moment. But yeah, as you can tell, I'm still traumatized by it. But and you don't want that happening to the layers of the sun shield. That's what I'm saying. And
no.
so apparently not. Apparently it all, the engineers did their job right, and they're some of the best engineers in the world working on this. So, but still, it's so easy to miss something. Right?
Well, and let's reiterate for people. I mean, if there was a tear or like any little mistake, there's really no way to repair it.
That's right. This thing is out at L2. It's well beyond where, say, the space station is, or something like that, right? And even if you could send a spaceship out there to go and futz with it, there'd be a huge risk of contaminating the very clean. I mean, one of the other things we haven't even talked about, right, is the challenge in making a telescope like this. Is the mirrors have to be super clean and free of contamination, so that they reflect properly. You want to be very shiny, right? So similarly, the aperture doors on the cameras have to be. We have a problem with our Chandra spacecraft, which is out at not quite as far out in space, but similarly out in deep space, where there's some kind of organic gunk that's leaking from somewhere else in the spacecraft, right? And it goes, oh, I'm in space now. Where am I going to go? Oh, I'm going to condense on the coldest part, the coldest thing I can find, which is the camera lens. And so we've got this film. It's probably only a few atoms thick of gunk on our camera lens that is making us blind in certain X-ray colors. Now, fortunately, for most of our color range, that gunk is transparent and we're fine. But we've lost a certain amount of capability just because this tiny amount of contamination getting on the camera. And so that's the sort of thing that you worry about. And you definitely, do not want an astronaut putting a thumbprint on the camera, right? Do not.
Oh my gosh.
Yeah. Or breathing on it, right? Well, obviously in the space you can do that, but even like rocket thrusters with hydrazine, right? Putting chemical rocket propellant that would contaminate the spacecraft. So you'd want to be very careful. I mean, maybe someday we will go out and refurbish the spacecraft as technology gets better. We're not in a position to do that now, but 15 years from now, maybe we will. But you're going to have to be super careful while doing it, or you could just ruin the thing.
Well, Jonathan, I know that telescopes are your jam. So explain to us why Webb is so epic, and also what you're looking forward to with what it should be able to discover.
Right. So there's two things about Webb. One is that it's big, right? And so the bigger collecting area, the more light you capture, right? And so the fainter things you can see. Right, and so you're looking at incredibly faint things, and so you need a huge telescope to capture any light from them at all. And then it sees in the infrared, and the main reason we designed Webb to look in the infrared is that there's a phenomenon in relativity called the red shift. And the red shift is, people may know that the universe is expanding, right? The whole universe, the space itself is stretching. And one of the effects that stretching space has is, as light goes through space, it gets stretched in a weird way. In the effect that it has is that its color changes. Because in fact, red light is just blue light stretched. And so something that starts off blue, as it goes through the expanding universe from a distant galaxy to us, gets stretched and becomes red. And on a bigger scale, something that starts off visible ends up infrared. And so if you look at a nearby galaxy in normal visible light that our eyes can see, and you want to compare it fairly with a very distant galaxy whose light has come through the expanding universe, that light, the visible light from that galaxy is now, as it gets to us, it's now infrared. And so Webb's infrared cameras will see the same stuff in a distant galaxy as Hubble's visible cameras see in a nearby galaxy. And so that's one thing. And so the what we think our understanding the history of the universe right now, okay, is that the universe is about 13.7 billion years old. And that's when we had the Big Bang.
Wow.
And the universe expanded from that. It wasn't like, and the misunderstanding people have about the Big Bang is it wasn't that it was in one place and there's an empty space that the universe is expanding into. The Big Bang was everywhere. At the Big Bang, everything was hot and dense. And then the whole thing just stretches, but it's already everywhere, right? It's just that everywhere is getting a little further apart. And you had this fireball that lasted 100,000 years, something like that, that slowly expanded and cooled, because as you expand things, they cool. And so at a certain point, the fireball became cool enough to become transparent. And the light from, so this part of the universe where we live, right, the light that could now go through the universe unimpeded is now 13 billion light years from here.
Wow.
But the light from over there, 13 billion light years away, is just reaching us now. And the light from behind me, 13 billion light years away, is just reaching us now. And so the different parts of the universe that were the moment when the universe became transparent, right, the light from there is sort of still filling the universe. And it's what we call the microwave background radiation. And we can see that with special telescopes that see even beyond the infrared, because its visible light has been stretched so that it's even past the infrared and into the radio waves and the microwaves. And we study that with other spacecraft, and that's how we know about the Big Bang. And we see that there are little lumps in that glow from when bits of the universe were just ever so slightly denser and hotter than other bits of the universe. Just a little lumpiness, a little irregularity. And so if I'm a lump that has 1,000,001 atoms, and the lump next to me has 1,000,000 minus 1 atoms, I've got ever so slightly more gravity than the lump next to me. And so it pulls on me and I pull on it, but I pull a bit more, and so I steal an extra atom. And so now I've got 1,000,002 atoms and it's got less. And so that process runs away and the universe curdles just because of gravity. It gets lumpy, like if you're stirring a sauce and not enough, and right, the sauce gets all lumpy, right? And so gravity makes things lump, and that's how the first galaxies and stars form.
Wow. And
that takes a few million years to happen. And as the gas gets, you get these lumps that fall under gravity and get denser and denser and denser. And the only thing that stops them collapsing is that they get hot in the middle, because when you squeeze something, it gets hot. And it gets so hot that you get nuclear fusion, so seriously hot, right? And because there's a lot of gravity. And you get a balance between gravity and trying to crush it and nuclear fusion trying to blow it apart, and that's what we call a star. And so the first stars form in the first galaxies, and then you just simmer for 13 more billion years, and you get us, and you get the universe that we see today. And so what Webb is going to be able to do is, it won't be able to see the glow from the Big Bang. We've seen that with other spacecraft, but it will be able to see these first stars, we hope. At least the aggregate light in the first galaxies, and so that's really the one of the big challenges. But it's not one of these missions where it's just got one thing to do, right? Webb is a Swiss Army knife. It's got 4 different cameras with many different modes. And yeah, it's really great for doing what I just described, but it's also great for looking at things much closer to us.
Right.
And so there's a whole, so the first thing that they're going to do after they focused it and fixed everything and calibrated it, I mean, they're going to look at, like, you know, a star to make sure that the image is sharp so they can focus it up. And they're going to look at a bright sheet of stuff to check that the image is uniform and know how to correct the image so that you know exactly how sensitive every pixel in the image is. But then they're going to start doing science. And they have this thing called early release science, which when we started the Zoom, I had the file right here to remind.
I was going to say, I have some questions for you too from people tuning in. So
well, let's do those then, and then we can talk more.
Want to do that?
So yeah, let's do that.
Michael Maxey asks if the James Webb Telescope will be able to find and confirm the existence of big dark matter, and if it was around at the Big Bang.
Big dark matter. I mean, there is dark. I mean, so what we know. Let me say a bit about dark matter. So it's embarrassing that astronomers have mislaid about 90% of the universe. That when you look at the shiny things in space that we can see with our telescopes, the stars, and you look at how they tug upon each other with gravity, right? The more stuff there is, the faster it should move, right? The harder you tug with the gravity, the faster it should move. But things are moving much faster than they should for the amount of stars that you see. There's something else tugging on them. And that something else is what we call dark matter, for want of anything better to call it. And we've been looking since the 1930s to try and figure out what this dark matter is. And we still don't know for sure, but we're pinning it down, we've ruled out more and more things, and it looks like it's some kind of elementary particle, most likely, that isn't seen in our accelerators, that's filling the universe and just adding stuff without adding visible stuff. And so one of the things that we can do is look at the motions of distant stars and measure how much dark matter there is in different places by how fast the stars are moving. And there's another effect that the dark matter has, and that's a weird Einstein relativity effect called gravitational lensing. And gravitational lensing is if I'm a distant star and in between you and me, there's some matter, even if it's transparent, it has gravity. And the picture of me gets bent, the light coming from me to you gets bent by the gravity. And in the right circumstances, it can get bent so that the light that was going not to you, but to your friend over there gets twisted around so it also goes to you. And so I get magnified, right? And so background stuff can get amplified and magnified by the invisible matter in the foreground. And so you can actually see the effects of dark matter that way. And we've done that in a bunch of different. So one of the first observations that Webb is going to do is look at a galaxy called Abell 2744. Sorry, a cluster of galaxies. So there's a group of galaxies called Abell 2744 that, because this dude, George Abell, found like 3,000 of these clusters of galaxies. And so there's all this matter in these galaxies, but there's the dark matter between the galaxies as well, that's acting as a massive lens to focus, to amplify the light from even more distant galaxies behind it. So, you know, Abell 2744 is probably only like 1 billion light years away, but, you know, things that are 3 billion light years away get magnified by it on the way to us. And so by looking at that, we can both study these distant galaxies in more detail, but also measure the effects of the dark matter in the Abell cluster. And so that's one example of an early science project that that Webb will be doing, I think, using the NIRCam, the near infrared camera, which is one of its 4 cameras.
Okay, here's another question. Will Webb be safe from cosmic rays in L2?
Ah, that's a great question. Yeah, yeah. So, there are various threats to a spacecraft in space, right? Things like space debris, which we don't have a problem with out at L2 because there's so little stuff we've put there. Micrometeorites, but they're pretty rare. But cosmic rays are everywhere. And cosmic rays, what they are there's two main kinds, solar and galactic. And they're things like, they're elementary particles like protons, bits of ripped up atoms, let's say, right? That have been accelerated to incredible speeds, almost the speed of light, by energetic events either in the atmosphere of the sun or in some distant black hole or pulsar, filling the galaxy with these little bullets, these microscopic bullets of fast moving particles. And the main threat from that is that, over time they degrade electronics, right? If you irradiate the electronics, it's going to cause malfunctions. But also, just when you take a picture, the camera actually, these cosmic rays cause flashes in the camera that look like they're light, right? And so you think you've got a picture of like a star or something, and it's really just a cosmic ray that came through the back of the camera. And so you've got to correct for that. But there are subtle differences between what the cosmic ray does and what a normal light from a star does. And so it limits the performance of the camera, but it doesn't, you can get rid of them, right? Okay. with software. We can fix it in software. And there's shielding around the cameras to kind of minimize, to minimize as best we can the effect of cosmic rays. So yeah, cosmic rays are one of the concerns, but they shouldn't, unless we've done our sums wrong, they shouldn't really impact us in a significant way. They're just a pain in the neck that's part of the cost of doing business.
We have some really good questions this morning. A tree in the forest asks, what level of detail can we expect to see when the telescope starts looking at exoplanets?
Right. So even with Webb's amazing sharp imaging, there are very few exoplanets that you can actually take pictures of, right? Because the planet is so close to the star that it's orbiting that it gets lost in the glare of the star for the most part. But what we can do is we can use what's called the transit technique, where we look at the star when the planet is behind it, and we look at the star when the planet is in front of it, and we subtract those two images. And there's like a 1% difference between them, right? That's the planet. And not so much taking images, but taking what we call spectra. And so the spectrum is just, if you like, a dot, but taken in 3,000 different, slightly different shades of color. And so we make a rainbow out of the light. And the thing about the rainbow will have missing colors because different atoms in the atmosphere of the star or the planet like to eat very specific shades of color. And that leaves a fingerprint of missing colors that tells you what atoms have been doing the eating. And so by comparing that spectrum of the star with the spectrum of star plus planet and subtracting, you get just the spectrum of the planet. And by seeing which colors are missing, you can tell what atoms are in the atmosphere of the planet. And so, for example, this is a long story, right? But here's the punchline. You can tell, for example, whether there's oxygen in the atmosphere of that planet.
Wow.
And so that is the main kind of science that Webb is trying to do with exoplanets. There's a scientist at UC Santa Cruz called Natalie Batalla that has an early release project to look at these exoplanet transits. There are also, we are going to do some imaging of nearby stars, and we might see the exoplanets as little dots. We won't see, continents on them or anything. We'll just see a dot. Oh, we saw the planet, it's really there. But also we're going to image what are called debris disks. And debris disks are when a star forms, the planet forms out of the leftover crap, the construction debris from the star, and that construction debris forms like a huge asteroid belt around the star. And we can't see the individual planets, but we can see the accumulated light from that disk. And we can see, if we're lucky, we might say ripples in it, where there's like a ring where a planet is going to form. So we're going to study solar systems in formation, baby solar systems with Webb. And that should be really interesting.
Wow. That will be interesting. And hopefully everything works out. And I think some people might wonder, okay, so after Webb, what's next? And I wanted to talk a little bit about the LAVOIR. Is that how you say it?
Well, yeah.
LAVOIR.
So we just went through what we call the decadal survey. And the decadal survey, every 10 years, as the name implies, the astronomy community issues a report saying, this is what we think we should spend money on in the next 10 years. And there's lots of different things that this report discussed. It discussed, small telescopes. It discussed how to make our astronomy community more diverse, all kinds of stuff. But the main thing it picks is it looked at 4 big projects that we might do and review them. It picked 2 of those 4 projects called LAVOIR and HABEX, which were big space telescope projects to follow on. And it said, okay, we don't think we should actually do either one of these exactly, but we think that the community should take these ideas and merge them and make a future big space telescope that would follow on in the 2040s or maybe even later, to push the ability to see exoplanets and things like that. But that's not the immediate thing after Webb. The immediate thing, because last decade, right, we already were thinking about what comes after Webb. And so right now we're developing a telescope called the Roman Space Telescope. And the Roman Space Telescope, it isn't named after like the Roman Empire. It's named after an astronomer called Nancy Roman.
Oh.
And Nancy Roman is the mother of Hubble. She was the head of space astronomy at NASA in the early years of NASA, and one of the people who, more than anybody else, really fought to make Hubble, what was then the Space Telescope, happen. Like as early as the 1960s, right? She was working on this.
Wow.
And as a remarkable woman, I was lucky to meet her a few years ago when she was, I think, in her 90s and still active and still doing science. And so I think it's a great choice to name the next big telescope after her. And the Roman Space Telescope is a little different from Webb. It's an optical telescope for the most part, and it's Webb and Hubble are both like scalpels. They see a very tiny part of the sky at any one time in great detail, and Roman is going to have the ability to see like a wider area of sky, and it's going to sort of map out the distribution of galaxies and tell us a bit more about the history of how the universe evolved. So that's a major project that's coming up. There's another major project that the Europeans are involved in called Euclid, which is a somewhat similar telescope. And so Roman and Euclid are the big ones to look forward to in the next decade after we get the harvest from Webb.
Have you followed much about the Chinese telescope that they're developing?
Yeah, there's not too much about it yet. Yeah, so China has a plan that they're going to have basically the Chinese Hubble, and it's part of their space station program, strangely enough. I think the idea is that they're going to park it in an orbit similar to their space station so that it's easy for astronauts to do a commute from the Chinese space station to their telescope and back to change out instruments. You don't want it actually attached to the space station. That would be very bad because like I say, there's all kinds of stuff happening on the space station that would contaminate the mirrors. And every time the astronauts went on the treadmill, right, it would bounce the telescope up and down, and so it would fuzz out the pictures. So you don't want a telescope on a space station, but having it near the space station where you can go and fix it easily, that actually makes some sense. And so, I think it's unlikely that the Chinese, to be fair, the Chinese telescope will be even competitive with Hubble, because they haven't done a big space telescope before. This is their first try. And they should be capable of making the optics, the actual mirror part, but the cameras are really a high-tech thing that I think they don't have a lot of experience in, and so they're likely to be not quite as capable as the cameras on Hubble, much less Webb. And so I think this is a learning experience for them, and it'll get good science, but it won't be something that blows Hubble and Webb out of the water. I don't think
right
about that. So it'd be good to have more data. It'd be good to have them added to the sets of source of space information, but they're a newcomer to the field.
right.
I think the main space telescope powers are the US and Europe, and also Japan, which has an interesting sideline in X-ray space telescopes that are really good. There's a satellite called XRISM that they're launching in the next couple of years that will be a very useful addition to the world's array of space telescopes. So it is, it's all international. The Webb itself, right, is a collaboration between America, Europe, and Canada.
Right.
And so there's particularly a very big European involvement in Webb. And actually, the Webb is available to scientists around the world to use if they can convince NASA they've got a good project to do. And so in this first collection of what we call the early release science, most of the astronomers using it are from the US, but there are some from Europe as well who are involved in the various projects. There's a group from Amsterdam looking at protostars. There's a group from France looking at nebulae that are forming stars, and so on. And so there's people from around the world. There's one Japanese team who are looking at a thing called a Wolf-Rayet star that's a super bright extreme star. And so it is a very international project already. But yeah, interesting to see the Chinese get in the game.
I'm curious because I don't hear a lot about Canadian space. And so obviously, Europe, Canada, and the US. Can you explain sort of each of their contributions to Webb, roughly?
Right. And so, Canadian space, to say Canada was one of the first countries to build a satellite other than the US and the Soviet Union. Alouette 1 was launched in 1962. And Canada's most famous in space for doing robot arms, right? The Canadarm on the space shuttle and on the space station is that big crane that moves things around, right? That's got a big Canadian flag on the side, just so you don't miss the fact that it's called the Canadarm. But they've also done some interesting space astronomy over the years. They had a tiny little telescope that looked at oscillating stars and extrasolar planets that was the size of a suitcase that they nicknamed the Humble Space Telescope. And their contribution to Webb is the NIRISS, NIRISS, which is one of the 4 cameras on Webb. And NIRISS is a 4 megapixel camera that sees in the infrared and has some special little abilities that are making it a little different from the other main infrared camera, the NIRCam. And so they've bought into that by building one of the cameras. And then Europe, of course, provided the rocket to get Webb into space, but they also built a couple of the cameras, including MIRI, this super cold camera that operates on only a few degrees above absolute zero and sees further into the infrared than Webb's other instruments. And so and so that's the main contribution from the other countries has been the cameras, and the mirror part and the spacecraft part and the sunshade part are pretty much fully American.
Wow. I want to pause for a bit of trivia that I found on, I know, I feel like we should have a sound effect. On Twitter, January 8th as an important day in astronomy. And you knew obviously about it being Stephen Hawking's birthday, right?
Much missed, yeah.
And I want to get to that in a second, but also astronomer Johannes Fabricius, is that how you say it?
Fabricius, I think we call
Fabricius, he discovered sunspots.
Right, yeah. So, and there's a big crater on the moon named after him.
So his birthday, also January 8th. Also the demise of Galileo in 1642, January 8th. And then now...
He always made a big deal of having been born on Galileo's death day. He saw himself as that was an omen that he was Galileo's successor, right?
Right. And how eerie. I mean, I just feel like what's going to happen next year on January 8th?
Well, I keep meaning to do an astronomy calendar, sort of like the Catholic Saints' Days calendars, where every day has an astronomy themed thing that you can celebrate, because there's so much that you can do, right? So any day you pick, there's gonna be, stories like that.
Right. But if you pick January 8th, that would be, or it's already getting pretty full.
Yeah. There's a decent amount of stuff on January 8th, right? It's nice to remember, nice to commemorate these events. We have coming up another big day is January 28th, where we sadly remember the Challenger.
Yeah.
But we also remember the Voyager flyby of Uranus, and there are a number of other good things that happened on the 28th. We have I know that there's anniversaries galore in these things. I'm trying to remember. I think Galileo was born on the day Copernicus died or something like that. Wasn't there something like that?
While you researched that, I wanted to give my viewers a little background. So I went to Boston. What month was that? Was that August that I saw you, or September?
Yeah, that sounds right. I don't know. Yeah.
Well, I mean, pandemic time, everything kind of blends together. But I think it was August. I went to Boston. I met up with Jonathan, and I learned from you that you worked alongside Stephen Hawking. You definitely were in the same room as Stephen Hawking. So do you mind sharing a little bit about that?
Right. Well, I didn't write any papers with Stephen, but I knew him, and I think at a certain point, I got to the point where he kind of vaguely knew who I was, like I was that Bernard's graduate student. So I was on the outer circle. So I did my PhD in Cambridge with a guy called Bernard Carr, who is one of the world experts on mini black holes. And Bernard had been a PhD student of Stephen's. And so they were good buddies, and Bernard would go visit Stephen, and occasionally he would drag me along, and I was like this little student in the room where these people were talking important things. And so I was lucky enough to be on the fringes of a whole bunch of really interesting scientific conversations that Stephen had with his colleagues. And I did go to one class by him. He did a class on quantum cosmology that I went to. and a couple, you know, like I was good friends with a couple of his graduate students. So I kind of, you know, I was on the fringes of that world enough to kind of get a feel for it and see what was going on, and
Right.
you know Stephen before he was famous, because this was before A Brief History of Time, right? This was I think he was just starting to be famous. I remember there was a Nova program that they did where they were talking about his work, and if you see that Nova program in reruns, you can just see the back of my head at the back of the class. I'm there, but yeah, so so it was a very, very minor you know, cog in this cosmology enterprise that was happening at Cambridge in the 1980s, which was just so exciting to be part of, and really asking these really big questions about how does the universe evolve, and how does quantum mechanics affect the evolution of the universe. Stephen had these really exciting ideas about seeing the universe, the whole history of space and time, as a single point in a bigger space of possible futures and pasts, possible histories, and looking at, you know, the forces acting on the universe in that meta space. And so so we were talking about metaverses long before Facebook was, so that was a very exciting time. I migrated more towards a slightly more practical stuff, you know, in terms of looking at actual black holes in the actual universe, in the middle of quasars and stuff like that. And so I kind of moved out of that very theoretical piece of astronomy over the years, and so I'm not really working with that group of people anymore. But it was a really fantastic training to have at Cambridge in the 1980s. That was just, you know, not just with Stephen around, but people like Martin Rees, who now the Astronomer Royal, just a really insightful and inspiring cosmologist. And I recommend, Martin writes a bunch of really good books on cosmology if you're interested. He's got one called Just Five Numbers, which he talks about the basic parameters of the universe. So you know, who else was there at the time who was really exciting? I mean, you know, there were people who were looking for the first exoplanets. They hadn't found them yet. All kinds of really cutting edge stuff. And so I was just so privileged and so lucky to have been able to go to Cambridge at that era.
And I have more questions that I feel like I'm behind.
Okay, I'll try to be less.
No. I think that is just such a cool personal story, and thank you for sharing it. Because when I found out about that, I was like, wow, that's must have been so cool. Sten asks, when does Jonathan think Webb will be looking at TRAPPIST-1, high or low priority?
Ooh, you know, one of the annoying things about the Webb webpage is that they have the abstracts of the early science observations, but they don't always list the specific targets. So I know that Natalie McDowell's project is looking at a bunch of exoplanets in the early months, but I don't know which ones. And so I haven't managed to find the actual target list. So it's possible TRAPPIST-1 is one of those, but I don't know. But there are definitely going to be observations at some point of TRAPPIST-1, and there will be observations of similar solar systems around other stars very soon. So yeah.
Can you give us a little background of TRAPPIST-1?
Well, what's fun about TRAPPIST-1 is it's a system that was discovered by a group of Belgian astronomers, and they had some I think the T and the R, like transiting planet something. It's one of these cheesy astronomy acronyms, right? They had a project to search for exoplanets, and because they liked Trappist beer, which is this Belgian beer built by the Trappist, made by the Trappist monks, then they found a way to make their project initials add up to Trappist, and so they found this solar system that has a whole bunch of planets, and it was we know a lot of those now, but it was one of the first solar systems that was a bit like ours, and it had a whole bunch of planets, including some that were sort of in the nice Goldilocks zone where you could have liquid water and stuff like that. And so it's been the subject of a lot of study over the past few years because it's sort of this analog solar system.
I feel like this might be a two-part question. Should we send more telescopes to L2 halo orbits, such as using SpaceX Starship?
Right. Well, there's so yeah, I'll take the two parts of that question. Is L2 the place to, do we want more space telescopes? Hell yeah. Because, typically a space telescope like Hubble or Chandra or Webb is like 10 times oversubscribed. There are 10 times as many good science proposals submitted as can be approved. So there's there's a lot more good science that we could do if we had more telescopes.
Right.
And also every one of these space telescopes is slightly different, has slightly different capabilities, right? As we talked about with Hubble and Webb. And so you can't use Webb to do this observations that Hubble makes. You can't use Hubble to do the observations that Webb makes. They have different capabilities. So, so we do need more telescopes, and L2 is the right place to put them. And it's because it's so dark and cold there, because if you have a sunshade, you can cut out both the Earth and the Sun. The Earth and the Sun are the same direction behind you as you look out into deep space. And it's far enough from the Earth that the Earth doesn't heat you too much. It doesn't blind you too much, but it's not so far that it's hard to talk to, right? If you send it way out into like Pluto or somewhere, right, then you wouldn't have a big enough radio antenna to send the picture, to download the pictures back to Earth. And so L2 is the sweet spot as far as we can tell, and almost all the future space telescopes are planning to go to L2. And the second part is
Starship.
Yeah, right. Well, absolutely. If Starship works, let's get Starship working. Okay. We talk to me when you have something that can go more than 10 kilometers high, right? And so hopefully in a few years, Starship will be operational and will be able to launch big payloads into deep space. And at that point, it'll be an obvious vehicle to use to launch big space telescopes. And it'll be really nice because you can build something like Webb without having all this folding up nonsense.
I was going to say, would you still have to do some sort of origami folding if you were able to use Starship for something like Webb, or is it big enough?
Well, let's see. No, for the sunshade, you'd still have to fold it up, right?
Because, that's what I was thinking.
Because Webb is, and I'm quickly looking it up to get the number right. The sunshade is 20 meters across, and if I remember correctly, Starship's diameter is something like 10 meters. And so it still wouldn't fit, unfolded inside Starship. And also, I guarantee you, right, as soon as you make a bigger payload, one of the problems is that the size of the telescope tends to be more constraining than the mass of the telescope, right? And so as soon as you gave me a Starship that can launch like 20 tons to L2 or something like that, I'm going to want to build a 20-ton telescope that's going to be way bigger,
right?
Right? And so you're still going to have to fold it up,
right?
So I'm guessing, for the cutting edge, you're always going to have these challenges,
right?
But what I think is the case is that for something like for a Hubble 2, you could make it much cheaper to launch a Hubble 2. The limitation, right, of this is Starship is not the thing that transforms space astronomy, because even if the launch is free, building these telescope, Webb, right, was $11 billion. And less than $1 billion of that was the launch, right? So the launch is a minor component of the cost of doing a big cutting edge space telescope. So that's just the thing to remember.
I'm not sure how to say this person's name, but they want to know, when do they plan to build a spacecraft that uses our sun as a telescope?
Right. So this is back to gravitational lensing, I think.
Okay.
And there is a point about 500 astronomical units from the sun. So one astronomical unit is 93 million miles. It's the distance of the Earth from the sun. So you go 500 times further out. So that's more than 10 times further than Pluto.
Whoa.
Right? If you have a star off in the distance, the light from that star passes the sun and gets focused to a point by the sun. So you use the sun's gravity as your telescope to focus the light. And if you then sit at that focus 500 AU downstream, you can get a magnified image of the distant star. That's this idea. It's a bit science fictiony right now, but someday we might make use of that. And I haven't looked into it in detail myself, so I can't say much more than that. But yeah, there are some wild and crazy ideas that people are playing with for the next century.
I'm laughing because my cat just sneezed on me. Torelli says moon-based telescopes would be better, but then Wesley says moon dust would cover the mirror. So unpack why moon-based telescopes are maybe not a good idea.
Right, there are several reasons, and Wesley's right. One is the dust. And one of the things we've discovered very recently, a guy called Phil Metzger has done a lot of great science on this, is that when you suppose you land a Starship on the moon, as we're planning to do, right?
Right.
And it takes off again. The rocket plume kicks up the dust.
Mm-hmm.
And there's no atmosphere to slow that dust down, just gravity. And so what happens is dust from the landing site can get blown right on the other side of the moon.
Wow.
Right? If you are doing operations, rocket operations in the vicinity of the moon, you kick up stuff that goes a long, long way. And so your telescope happily observing on the far side of the moon, something gets a shower of dust on it from something happening on the near side. And so if the moon gets to be a busy place, as we anticipate it will, that's going to be a problem. There's another problem, even if you don't have activity on the moon, which is that the moon, the day and night on the moon lasts 14 Earth days, right? The day-night cycle is a month.
Wow.
So you have 14 days of sunlight and 14 days of cold and dark. And so the thermal cycling, right? You can design a telescope to operate in a very hot environment, and you can design a telescope to operate in a very cold environment. But it's really hard to design one that operates well when it's hot one day and cold the next, right? Heating up, cooling down. That sucks for electronics, and so that's a challenge. And I think there's a lot of interest in putting radio telescopes on the far side of the moon to shield them from radio transmissions from Earth. And that might be a good thing to do. Radio telescopes aren't so delicate. You could lay out a huge radio telescope miles across on the far side of the moon and not have all the radio interference that we currently have for radio telescopes on Earth. for a while. But then again, if Elon's vision has come true, or if even NASA's vision has come true, there's going to be a whole bunch of spacecraft squawking in various, radio bands in the vicinity of the moon pretty soon, right? And so our nice radio quiet zone isn't going to be radio quiet for much longer. So it's still maybe okay enough to be worth doing, but it's not, the radio astronomers might end up having to go out beyond Jupiter or something like that, because you really don't want to be where the people are.
Johnny Spacer wants to know, could a space telescope be built in space?
Well, that, so more or less, and the question is, what's the cost benefit, right? And so, for example, if you were on an asteroid, you can imagine using asteroid rock to make glass and make a mirror and polish it like amateur astronomers do, so it's not like you couldn't, but the level of, and someday we'll have already the level of industry, because we're doing other things, like maybe we're mining on that asteroid, and so we have heavy equipment there already. But I think for the foreseeable future, it's going to be easier to use Earth materials and build it on Earth and send it out. Expensive as that is, it's not as expensive as building the telescope making machinery and taking that out and then building the telescope there. Now, there are intermediate things. You can imagine making a big telescope like we did the space station, right? We built the space station. Individual modules were built on Earth, but then we stuck them together in space.
Right.
And so that's an approach that you can imagine doing. And the trick there, as we saw with Webb, is that the alignments have to be so precise, right? So it's sort of like, we've all had this experience with IKEA and stuff, right? Of piece A is meant to fit into piece B and it doesn't quite fit, and you have to drill out a bigger hole, otherwise it won't work. And prefab is only good if the tolerances are very tight,
right?
And so it's easy to get wrong, right? You don't want to go out into deep space and find that your two pieces of the telescope actually don't quite fit together. And so, maybe we'll take that approach to make bigger telescopes by launching them in smaller pieces and rendezvous and docking them. But you got to be, it's tricky, and it's tricky to align them to the wavelength of light precision that you need in a telescope. So we'll see.
I actually like this question from Nick's hobby channel. He says, this might be a stupid question, but why would they put a 4 megapixel camera on the James Webb Telescope when something like an iPhone has a 13 megapixel camera?
I wonder if someone else, yeah. Well, but this is a 4 megapixel infrared camera, right? The technology of this camera is not consumer technology. It's way ahead, right? It's way more sensitive than an iPhone camera. And it uses a different kind of light. It's generally different technology. So we can't yet, the answer is, we don't have the technology yet to build a 13 megapixel infrared space camera. We're getting there, but I remember where infrared cameras, you were lucky if you had a 30 by 30 pixel one, like 100 pixel camera rather than any number of megapixels. So infrared cameras have come a long way, right. But they're behind the optical cameras in that sense. And so all of the cameras on Webb are about, one of them, actually Miri, I think, is only 1 megapixel.
Wow.
NearCam is 16 megapixels. And Nearest is 4 megapixels, so they're very, they're in that range of 1 to 20, kind of thing, right? They're depending on things, but they're all, each of these cameras cost millions of dollars to build, even with that many megapixels,
Right.
So it's they really are cutting edge, and we're very happy to have that many with this technology.
Yeah, I don't think that was a dumb question at all. So thank you, Nick's Hobby Channel. I had the same question actually myself. Alonzo writes on Twitter, this is a must-watch live stream featuring Mr. Orbital Police himself. So congrats on that. Eric wants to know, won't micrometeorites damage the mirrors at all? And I think you talked about that a little bit. You just say they're kind of rare, right?
Yeah, and so there will be little micrometeorite hits, right? Again, but they'll be, you can't, as long as 95% of the mirror is still shiny and polished, right? Then the occasional little ding won't distort the image very much. And just like in my glasses right now, there are various bits in my glasses which are dinged or which have crap on them, right? But I can still see you. You're still in focus for me, and it just cuts the efficiency very slightly. And so the thing you really don't want, right, is contamination across the whole mirror, but a little spot here or there actually doesn't matter that much, as long as the mirrors stay aligned.
Right. Alex Kusenza has a question that I feel like I get a lot. Is it possible to mine material from asteroids?
Yeah, well, it is, and we just did it actually twice. There's a Japanese mission that mined a coffee cup full of material from asteroid Ryugu and brought it back to Earth last December. And the American OSIRIS-REx spacecraft did the same thing on an asteroid Bennu, and it's heading back to Earth right now, getting there next year, I think. So it's an exaggeration perhaps to call that mining when you just get a coffee cup full, right? But it's a proof of concept, and so you just have to scale it up. And we have, I think the next few years are going to see some very exciting asteroid missions. We just launched Lucy, which isn't going to do any mining, but it's going to prospect some of the Trojan asteroids near Jupiter, or in the orbit of Jupiter, to find out what they're made of. And similarly, another prospecting mission called Psyche is going to launch, I think this year or next. I think this year, yeah. And it's on its way to an asteroid called Psyche, which is made of metal. It's one of the first metal asteroid that we've visited. And so we're at the stage now where we're prospecting the asteroids to see which ones have which minerals, and we're mining at tiny levels. We're getting what we call sample return missions to bring stuff back from asteroids for scientific purposes rather than to get the ore, right?
I was going to say, when do you think it'll transition from scientific purposes to making money and getting these resources?
It's going to be a while. The first generation of asteroid mining companies all went bust in the last few years, as far as I know, and because they were just a little too ahead of the curve. But yeah, maybe 10 years from now, maybe 20 years from now, it's just a matter of making the business case close, right? That's the trick. It will eventually be economic because space travel will get cheaper, and platinum and other rare elements will get rarer on Earth and more valuable, and we'll have more uses for them. And so at some point it will be profitable to get them from the asteroids. So it's
This brings me to my next point, and actually Alex replied saying, cool, so the movie Don't Look Up wasn't far-fetched. And I'm going to put you on the spot. Have you finished watching it yet?
I haven't. I'm
okay,
half an hour in right now. I'm watching it in little bits when I have time.
But you know the general concept, right?
Don't spoil it for me. I don't know what's going to happen.
What do you know about the movie?
Well, it's asteroid's going to hit, or a comet's going to hit the Earth and kill us all.
Okay.
And no one cares because they don't want to deal with it. It's sort of a climate change analogy, right? It's like,
yes,
something bad is happening, and the people who know about it can't get anyone to pay attention because. So that sounds very familiar. And I think, yeah, I mean, the bit I've seen so far is pretty realistic. They've did some observing. They did the orbit calculations. They get an answer that is, I think, they haven't talked a lot about the uncertainties involved, but you can imagine a situation like that where you do the math, and normally the math tells you, well, this might hit Earth, but probably it won't. Like there's it's going to come within 100 miles plus or minus 1,000 miles, right? And so, probably that could hit Earth, but it probably won't. But you might get one where the measurements are accurate enough and it's aimed right enough that the answer is, oh, it's going to hit the Earth to within, 100 miles plus or minus 10 of the center of the Earth, and it's going to for 100% certainty hit the Earth, or at least 99% certainty. And if it's a big enough one, and that's the unlikely thing. The more likely thing is I worry not so much about the extinction level event. I mean, it could happen, but it's unlikely. But what you might see is like a city buster. Mm-hmm. Where you go, oh yeah, okay, there's something that's going to take out Florida, say. It's not going to take out all life on Earth, but it's going to take out all life in Florida. If you're in Florida, I'm sorry, I'm just using it. And so that could happen.
Well, I have follow-up questions for you that I will not spoil. So we'll get off the don't.
Yeah, give me another week to kind of get around to watching the rest of the movie.
That just means that you guys all have to tune in when I finish asking those questions, because I have some great questions for you about that. And we're just getting so many questions. You're Mr. Popular this morning. I hope you're not too tired to answer.
I'm good to go. Keep them coming.
So DS wants to know, what is your most likely solution to the Fermi Paradox?
Oh, that's a hard one. Yes. Ellie, do you know the Fermi Paradox?
Vaguely.
So the Fermi Paradox, so Enrico Fermi, right, was the Italian-American scientist who made the first nuclear reactor in the 1940s at the University of Chicago. And his take on aliens is, where are they? That's the Fermi Paradox.
Right.
Because if you just do the simple math, right, the galaxy is billions of years old. Even if you have our technology, you could build like generation ships that would get between the stars in times of tens of thousands of years, right? And so you can imagine building a society that, took 10,000 years to get from the Earth to another star, and people would live and die on the ship, and there would be whole civilizations rise and fall on the ship, but eventually it would get to another star. And so it might take, and then in like 10 million years of doing that, you could have humans in every solar system in the galaxy, right? And 10 million years is not a long time. Right, by astronomy standards. And so why hasn't anybody done that? Why aren't there aliens all over the place shopping in our shopping malls and visiting us as tourists, right, all the time? And despite the UFO fans, it does, there's no evidence that is actually happening. And so it's actually surprising it's actually, on the face of it, a bit surprising that we don't see aliens all over the place. And so the possibilities are, life is very rare, or intelligent life is extremely rare. So we are the only sentient life forms in the galaxy right now,
which is kind of terrifying.
Right. Well, that's it. I mean, maybe the civilizations don't last very long, so there have been others, but they're all dead now.
Right.
We're the only ones right now. That's possible. Another possibility is what they call the zoo hypothesis, which is that they are everywhere except here because they don't want to culture shock us. We're not ready for it yet. And so there's like a keep out sign around the solar system to go, don't disturb the inmates, right?
Well, they're probably right. I think we would all
we're like a wildlife preserve. Yeah.
Don't you think we're not?
It could be bad for us. Yeah, absolutely, right. And occasionally, alien teenagers break the rules and buzz us, and that's where the UFO reports come from, or something, right? So that's one possibility. Is they're there, but they're protecting us. But it's surprising that we don't see obvious evidence of like star systems being engineered or something like that, right? People moving, super advanced aliens moving planets around, and so there's some limit on how advanced the civilizations can be, that we don't obviously notice them in the galaxy. And so there's a bunch of reasons why we might not see aliens, but the kind of the null hypothesis, if you like, the most obvious Occam's razor simple explanation is that they're not there, and that we are alone, at least in this part of this galaxy. And the nearest other, I'm sure there must be aliens somewhere, but maybe they're not in this galaxy. Maybe they're so far away that the distances are just impractical. But also, the idea that civilizations don't last very long, and if you say, how long does a typical civilization, like a typical intelligent life form, last, right? Well, we have one example, us, and how long are we probably going to last? Well, it's not looking too great right now, and so maybe if we're typical, civilizations destroy themselves, and they're not really very evolutionarily adaptive, and so that's a possibility, and that's why we're not seeing them. So I don't know the answer.
Come on, the answer. I'm just kidding.
Yeah.
All the answers.
Yeah, I would say it's probably some combination. That the time scale, the main thing, as I think I've said to you before about aliens, right, is the time scales.
Yeah.
That we are, as a species of Homo sapiens, 30,000 years old, depending on how you count it, right? And so we're a very baby intelligent species. And if we meet aliens, how long will they have been an intelligent species, right? So right. If you just sort of roll the dice and assume that it's equally likely that a species is, if species last a long time, so they can be any age, and you say, and that they can have formed at any time in the past, maybe billion years, because before that maybe there wasn't enough heavy elements in the universe but even then there's maybe 5 billion years is a reasonable time scale. You have to have some time for the planet to get nice enough to have the conditions for life and for the intelligence to evolve and so on. But the universe is 13 billion years old, and it's had heavy elements in it for most of that time. So you can say it's equally likely that the species are between 0 and 5 billion years old. And so the chance that they're exactly born at the same time as us is tiny, right?
Right.
And so most likely they are at least hundreds of millions of years ahead of us. Right?
Yeah.
And the analogy I make is, suppose you go to the mall again, and you talk to the first person you meet, and you ask, and you discover that not only are they the same number of years old as you, but they were actually born on the same day and the same hour. That would be really surprising.
Yeah.
And that would be the equivalent of meeting another species that was only a few tens of thousands of years old, right? Because the universe is so old that it would be really surprising if they were exactly the same age as us.
Right.
And so, and if they're younger, they're not even intelligent yet, so they're not going anywhere. And if they're older, they might easily be hundreds of millions of years older. And so the betting is that if you meet aliens, they are super, super advanced compared to us, and you don't want to mess with them. Right.
Or they don't want to mess with us. I don't know what's sadder, the idea
they
that
don't even see it. I mean, they maybe don't even consider us as counting
right.
as intelligent, right?
But if they do, and there's just this keep out sign, like, don't go there, they're gonna
yeah
crumble.
So that's my take on aliens. Yeah.
I feel like we could go on and on about that one. Vaughn wants to know, on the NASA webcast, I heard that Webb will also study targets in our solar system. What's the advantage of having Webb do that over our other methods of observation?
Right, because in our solar system, we can actually send things there.
Yes.
On the other hand, each mission we send there is, $100 million or something like that. Whereas diverting Webb for an hour to look at it is significantly cheaper. So in the early release observations, the only solar system target is Jupiter. They're going to look at Jupiter, I think, and its moons, and look at it in the infrared in more detail than we've been able to see, because the space probes that have gone to Jupiter, I don't think have infrared cameras on them. And so this will be a new color to look at Jupiter, a new lens, if you like, to look at Jupiter in. And so there are things that Webb can do that we can look at. I think you can look at comets, for example, which come through the inner solar system in for only a few months. There's not time to send a mission to them often if they're fresh new comets. And so there are various things in our solar system where Webb can play a useful role. I think it's not the primary use of Webb. It's like 5% of the observations might be in our solar system, say, something like that. It's a thing that Webb will occasionally do.
Want to get to this question from Bayerwald. How big is the risk that worn out reaction wheels will limit the operations of Webb? Kepler and Hubble ran into serious problems.
Yeah, there was a bad batch of reaction wheels. So what are reaction wheels? Reaction wheels are the way. So this is a good opportunity to tell you how space telescopes look at things. Suppose I'm staring at Jupiter with Webb, but now I want to stare at the Andromeda Galaxy instead. So I got to turn Webb in space to look in a new direction.
Okay. Yeah.
So I could use rocket firings to do that, but that's really wasteful and has all kinds of bad things. What I do instead is inside Webb, I have little wheels that are whizzing around powered by electric motors. And one wheel is spinning this way, and one wheel is spinning that way in X and Y, and another wheel in Z. And so now I change the speed at which the wheel is spinning. And there's a thing called conservation of angular momentum, which says if I change the spinning wheel speed, I've taken out angular momentum. Webb will start turning the opposite direction to compensate for free, right? And so by adjusting these wheels, I can make Webb turn around. It won't change its orbit, but it will be pointing in a different direction. And that's fine as long as those reaction wheels keep spinning. But if they break, then you're in trouble. But you have probably, I don't know how many backups it has, but it has more than one set of these. So right. It can afford, you always have at least an A side and a B side. And if the A side breaks, the B side takes over for each wheel. And so that is how we point telescopes. And yeah, we did have problems with Webb and with Hubble and Kepler. But for example, with Chandra, we had one wheel go bad after 20 years. You know, but we're mostly still good. Touch wood. The modern reaction wheels are more reliable, we think. Yeah, let's cross fingers on that. But, and so yeah, so the first line of defense is we have more than one set, and the second line of defense is we don't have the crappy ones that we had for Hubble and Kepler. We bought the good ones, and so hopefully they'll do us proud. But
yeah, Jason says they break, then you have a $10 billion paperweight.
Yeah, well, that's a bit of an overstatement, but yeah, if they all break, I mean, so for example, right, with Kepler, you know, we had the K2 mission afterwards, where enough of the wheels had broken, we were down to like one wheel, I think, that we couldn't point it the way that we could before, but we could still point it well enough to do some other science. And it operated for several years doing, you know, on like one wheel, doing slightly less accurate pointing. And so I think that, you know, there are degraded modes where you could still operate, but you wouldn't be able to do everything that you wanted to do.
Right.
But I think, you know, I'm not too worried about that. I mean, I think it might be a life limiting thing, like 10 years into the mission, we might see reaction wheels fail, and we might have to go to a degraded mode where we can only do certain observations but not other observations. That's the sort of thing you might see.
Let's see where. Charlie wants to know, why hasn't any satellite or rover been sent to Europa and beneath its icy surface to search for life?
Right. Well, so there's two questions there. Why not to the surface, and why not beneath the surface?
Yes.
So there's been discussion of a Europa lander for many years. It's a multi-billion-dollar mission is the basically the answer why. And there have been some people there's certain congressman who's been trying to put it in the budget every year for the past 20 years. I think he's retired now, but and it keeps getting cut out because it's not the highest priority for compared to other missions. Drilling through the ice, I mean, the ice is probably miles thick, so I don't know how I don't think we have the technology to drill through the ice and see below. And so that is, I think that's for another generation. But a Europa orbiter where we can study Europa in detail, that is happening, we think, and that's I forget exactly what stage it's at, but it's in the plan for the years to come. So we will be going back to Europa. There is a kind of a struggle. I don't want to overstate it, but there's a bit of a tussle between the folks who want to spend all the planet exploration money on Mars and the folks who want to study the outer planets.
Yeah.
And there's only so many dollars to go around, right? And so there is a bit of a feeling that the Mars folks have had a bit more than their share of toys, and it's time to do a bit more with the outer planets now. And so at least there's a bit of that feeling among the outer planet scientists, and the Mars people think that no, they should get all the money, and so we'll see how that plays out. There are some outer planet missions underway. I think next year is the JUICE mission, Jupiter Icy Moons Explorer. No, I can't remember exactly the acronym, but it's a European mission to explore the moons of Jupiter. So Europa will get some love there. Juno, of course, is still in orbit around Jupiter. There's other missions. The Dragonfly mission is going to have a rotorcraft on in the atmosphere of Titan, looking at the moon Titan of Saturn. so there's a lot of exciting things that are being done even within the outer solar system gambit that are competing with Europa missions. But there isn't a Europa mission in the works, but it's going to be a while.
You're getting a lot of thanks, by the way, for your answers. And it makes me want to ask you, do you think that we need more money into our space programs?
Well, I mean, I think that the amount of money we're spending on space is relatively less, certainly on space science, let's say. Let's distinguish between the money we're spending on astronauts and on exploration and the money we're spending on science missions like astronomy and planetary exploration. And I think that, you know, over the years, there's been relatively little, the amount we're spending on those science missions is not as much as it once was, I think, and is, you know, allowing for inflation and all that. But on the other hand, you know, I mean, I don't want to overstate that because I think we can. We're the richest, the US, talking about the US program, we're the richest country in the world. There's lots of things that we can afford that we're not doing. I wouldn't want to sacrifice, you know, the social programs, the economic programs, right? Our country has a lot of problems right now.
Right.
We need to address them. On the other hand, we're wasting a lot of money too, not least on some of the aspects of the military budget. You know, we need a military budget, but I don't think we need as big a military budget as we have. And there are other things that, you know, you could see reassigning. So, and you know, you could actually tax the rich a bit more as well. And so I think that there is scope for freeing up more money for fundamental research, and space science is part of that. And I think it is valuable to understand the solar system that we live in,
right?
To research things like Don't Look Up, right? Research the incoming asteroids that might hit us. But also just to understand, you know, we need to understand the Earth, right? Climate change needs a lot more money thrown at it, and to understand the Earth's climate, one of the ways that we've understood the Earth's climate is by looking at the climate on Venus. Right. And comparing it, right? Because if you only have one example of something, you don't know what is generic and what is specific to that situation, right? So in other words, if you only know one person, right, you don't know what are the quirks of that person or what are like just human things that all humans do.
Right.
So if you want to understand, you know, medicine or something like that, you don't look at one patient, you look at 1,000 patients. Right. And so that's one of the immediate values of our scientific exploration of the universe, is that Earth is an example of a phenomenon that happens in various places in the universe. And we need to understand more broadly how the universe works to understand how the Earth works. You understand planets means you understand the Earth, and the Earth is fragile right now, or the biosphere on the Earth is fragile. Earth itself is solid. And so, you know, I do believe that it is very important that we fund these studies. It's also important that we fund, you know, more medical studies and more, you know, virology is particularly interesting right now, vaccine studies, things like that, right? And so I don't want to say you should take the entire US budget and throw it at space, right? It's you have to balance things.
But a little more.
But a little more, I think, would be reasonable. Yeah.
All right. We have tons of questions. Raj Luthra says, hello, Jonathan. Do you think we will see Artemis 1 and Starship Super Heavy launch this year?
Yeah, I think so. If you'd asked me that a year ago, I would have said, no, I don't think we'd see it launch in 2021, and I'd have been right. But they're getting close now. Definitely, I would be surprised if SLS Artemis 1 does not launch this year.
Okay.
If I would say, even, I'd be astonished if it doesn't launch this year.
All right.
Starship, I expected to launch this year, but I wouldn't be astonished if it didn't, because you know, it's such a new design. There are things can happen, right? Or it could run into trouble with the FAA or something. So there are scenarios in which Starship doesn't launch, but I think it's unlikely. I think you know, by the fall maybe. Yeah, I think it could get delayed some more, but I think sometime this year one would expect Starship to make its Starship Super Heavy to make its semi-orbital flight. I do not think that we will see the full recovered Starship. I mean, so the sort of full Starship, right, is Super Heavy boosting Starship into a proper multiple orbit loop around the Earth, and then Starship coming back down and landing intact, ready for reuse, right? That, I think, is not going to be this year.
Marina wants to know, how are things going with Voyagers?
Right. So Voyager 1 and 2 were launched in 1977.
Wow.
And they were boosted on this interplanetary billiards trajectory, we called it, that bounced off Jupiter and Saturn, and then in the case of Voyager 2, Uranus and Neptune. And they are now well beyond Pluto. I think they're about 100 astronomical units out now.
Wow.
And so they're heading out to the outer parts of the solar system. They're actually feeling the interstellar wind now. So they're still within the gravity of the sun, rather than the gravity of other stars in the galaxy. But the environment that they're in is really interstellar space. They're tasting the gas that's kind of come from other stars rather than the gas that's associated with the solar wind. And they are continuing. You can actually follow them on Twitter. Voyager 2 tweets occasionally. Well, I mean, obviously, you know that it's a bot that's driven by data from Voyager 2, but and so yeah, they're powered by these things called RTGs, radioisotope thermoelectric generators, which are thermocouples running off a lump of warm plutonium. And so it's not a nuclear reactor, it's just a warm plutonium that's warm because it's undergoing radioactive decay, and that heat you can get electricity out of. And so that's keeping them alive for long periods of time, but they're running down slowly. The signal is getting fainter, and they're getting further away, so the signal is getting fainter. And so it's not clear how much longer we'll be able to talk to them. But for now, they're sending back useful scientific data about the conditions of the interstellar plasma that they're flying through.
Wow.
So that's a 1977 era. I mean, you'd be happy if you had, like, you know, a Ford Escort from 1977 that was still running.
Yeah.
And have a spacecraft that's still running after all that time. They built them well.
That is crazy. Another good question from Raj. He says, when do you think humans will explore Uranus, Neptune, and their moons again?
Right. Well, obviously, you know, so far we've only sent robots there, right? So we're talking about humans sending their robots to explore the outer planets. And I hope, you know, I mean, soon, bearing in mind that it's going to take, you know, 10 years from launching to get there. So it's going to be a while in that sense. But I'm hoping that it's time. It's time to go back and explore the ice giants. That's what they're called. So we have Jupiter and Saturn are the gas giants, and Uranus and Neptune are the ice giants. And they're a different kind of planet. And we haven't studied them well, and they have interesting ring systems and moon systems that are, you know, also of interest from phenomena like cryovolcanism, liquid or solid nitrogen volcanoes, things like that. The cold outer system. There's a lot of science to do there. So we should fund a mission to the outer planets to study either Uranus or Neptune. And there have been various proposals over the past few years, but none of them have gotten selected. So we just hope that every few years, right, NASA does a discovery mission and a new frontiers mission selection where science teams propose specific missions, and then they pick one to be developed and eventually launched. And so that's a way of getting the best ideas. And there's a sort of jury that goes, well, which will give us the better science, the Uranus mission or the Titan mission or the Jupiter mission, right, or the Venus mission.
Right.
And so that's so far the outer planets missions, the ice giant missions haven't won any of those competitions, but I hope that will change.
Do you think it's currently possible for humans to explore interstellar space with modern technology? So I'm guessing he's talking about humans this time.
Yeah, well, I'm not sure. I mean, I think maybe it means we're also sending probes, because we haven't even done that. The Voyagers are our first, messengers into interstellar space that are actually sending back data. We sent the Pioneers out to interstellar space, but they were dead by the time they got there. I mean, that was not their mission. Their mission was just to get to Jupiter. But then, yeah, and so, let me jump ahead to say the next step beyond interstellar space, right, is other stars, right? Mm-hmm. In particular, Alpha Centauri is the nearest other star system to our suns, 4 light years away. And just around Pluto and like New Horizons probe, right, we've gotten like a few light hours from Earth. And now we're talking of jumping to light years. And so there are some studies underway. There's this crazy Russian billionaire called Yuri Milner who threw a lot of money at the breakthrough prizes, and he's funding people like your friend Avi Loeb to study Project Starshot, how you could send a tiny little micro probe about yay big to go past Alpha Centauri and send back some information, right? And so we're at the stage where, people are throwing around these ideas, but we're not really ready to do it.
Okay.
We're ways off from actually having the practical technology to do it. We're asking the question of what new technology would you need to be able to do this?
Right.
And so I think it's a while.
This question kind of makes me laugh. Charlie Nelson wants to know, is the multiverse real or bro science?
We don't know. I am skeptical about the multiverse.
Okay.
It depends. I mean, the other thing is, right, there's like 5 different things that are called the multiverse, 5 different science fiction-y ideas. And so you got to be more specific about which one you're talking about. So there's a possibility, for example, that our space-time that we can see, our universe, is not there. Like there are other such space-times that are essentially infinitely far away from us and connected through the Big Bangs to an underlying universe. And that's just saying that our universe is actually a lot bigger than we think it is, and there are bits of it that we can't get to. But that's different from a multiverse where you're like on Sliders or something, right? Where you're imagining, maybe that's too old a science fiction reference, where you're imagining multiple copies of this universe that are slightly different from each other, and you could kind of, teleport from one to the other and find a universe in which, history had played out differently in some way, right? And that people have sort of thought that was possible from what we call the many worlds interpretation of quantum mechanics. That quantum mechanics says every time an atom decides to split or not, you can imagine that actually it makes both decisions and creates a new universe every time it makes that decision.
Oh my gosh, yeah.
You know, and you can interpret the math that way. And so then you have an infinite number of very similar universes, and you can imagine being able to go from one to the other and you know, find the Ellie who decided that instead of becoming a TV anchor, she would be an airline pilot or something like that, right?
All right.
And so, you know, that's I can't disprove it, but I'm skeptical of that one.
That just quick segue that reminds me of the German science fiction thriller Dark. Have you seen that show?
That one I don't know. I'll have to.
You've never heard of it? Okay.
Yeah, I don't know.
Folks in the comments, I loved Dark. Please let me know if you've seen it and you like
Dark?
it. Dark, like dark matter.
Light. Yeah,
Yes.
okay.
You should.
I'll have to check that out.
Kind of deals with like time travel and this idea that there's like different versions of you and like the same universe. And
okay. Yeah, I mean, you know, it's an old idea in science fiction, right? But it's always nice to see it done well.
It was done very well.
Yeah. There was, I did see there was a show called Dark Matter a while back that was a really good science fiction show that I'm still bummed didn't get renewed. So I recommend that one to people.
Is The Expanse your favorite show? Like
of the ones currently running, maybe. I mean, Babylon 5 is still my favorite sci-fi show, and they're rebooting that, so I'm very excited.
Okay.
And Doctor Who, I'm still a fan of Doctor Who. I've been watching for 50 years.
I did see your collection. It was quite large. Raj wants to know, I think you might have answered this earlier, but when the 6 months have passed, what is the first image or first images we will get from Webb?
Right. Well, I've been talking a little bit in this show about the early release observations. We don't know yet what order they're going to be taken in, because that's going to be decided actually much closer to the time, right? They have this pool of, we know we want to look at these things. What order you look at them depends on sort of optimizing exactly where Webb is in its orbit at that time when they get ready to do it, right? And so if Webb ends up starting those observations a week later than it otherwise might have done, it'll be a totally different order. And so just of the constraints of where the sun is and where the objects are and what the thermal constraints are. So it's not that they're not telling you what the first image is going to be. They genuinely haven't decided yet, but they have decided on the portfolio. And so I looked up, and the images that they're taking in the first, what they call the early release science, they're going to look at a gravitationally lensing cluster of galaxies. They're going to look at 4 what we call luminous infrared galaxies, which are galaxies where for some reason there's an enormous amount of baby stars being formed all at once. So they're going through what we call a starburst. They're going to look at a bunch of exoplanet debris disks, like I mentioned. They're going to look at Jupiter. They're going to look at some star-forming nebulae. They're going to look at a nearby dwarf galaxy called Wolf-Lundmark-Malot, and a globular cluster called Messier 92. And they're going to look at a blank bit of sky. And that's actually one of the most exciting ones. Hubble did this too. There's a thing called the Hubble Ultra Deep Field that you may have seen the pictures of. Yeah, that was basically you take a bit of sky when there's nothing interesting in ordinary telescopes, and you look at it with your new Wizzo telescope for a long time, and so you're seeing like the stuff that you couldn't see before, right? So you stare at a blank piece of sky for a long time, and you see the faintest stars and the faintest galaxies, that are further away than that didn't show up in the previous generation of telescopes. And so I anticipate that deep field, the CERS it's called, will be one of the interesting early results from Webb. But on the other hand, the Abell 2744 we have nice pictures of from Hubble. We know that's going to be really pretty, you know, these infrared galaxies. A lot of these luminous infrared galaxies are actually where two galaxies have smashed into one another. They're like big cosmic train wrecks, and so they're often quite pretty as well, as long as you don't have to live in one. So I think, you know, that's and then the other aspect, right? Remember, Hubble Webb also takes spectra, right? And the trouble is, the spectrum is very disappointing to the public. It's basically a wiggly line with, like, you know, spikes in it and stuff. It's the meat and potatoes of astrophysics, because it tells you what the objects are made of, how fast they're moving, wow, how hot they are, but it doesn't, like, it's not like a pretty picture. And so we're going to take spectra of quasars and galaxies and exoplanets and protostars, and that's going to be the scientist. My fellow scientists are going to look at those coming out and go, "Ooh, that's really cool," and the public's going to go, "That's a wiggly line. Why do you spend billions of dollars on a wiggly line?" So you know, so I think the public's going to be interested in the imaging data, and that should be pretty nice. Yeah.
Wow, that you make a good point. You know, and you've been interviewed by all the major networks. Is this the longest interview you've done?
How long have we been going now? Wow, 2 hours.
2 hours. Right?
Yeah. I've done a couple 2-hour you know, podcasty type interviews before. Yeah, right. So this is getting up there, but
well, I mean, we're just so grateful because you are just this wealth of knowledge and information, and I love how you always have an answer. So if you guys have questions, make sure to get them in, because I don't want to keep you on the line too long here. Someone did ask.
Soon.
Well, you have to eat lunch soon.
Yeah, in the next half hour, you know.
What does Jonathan McDowell eat for lunch?
I'm probably just going to make myself a roast beef sandwich, and then or I might order out for Grubhub to send me some sushi.
Oh, yes, I support that 100%. Graham wants to know, will Webb be able to observe Oumuamua, or is it too far away by now? And will it be able to observe similar objects in the future?
Right. So I don't know how bright Oumuamua is right now. That's a good question. It's also, I don't think it's not clear what Webb can tell you about Oumuamua. You know, the most likely thing you'd want to do with it is, you know, it's too far away for Webb to actually take a useful picture, right? It'd just be a dot. And so you could take a spectrum, an infrared spectrum, and that might give you clues as to what it's made of, but I'm not sure it would tell you much more than the optical spectra we already have. So it's not clear that Webb's the right instrument to use for Oumuamua. Again, we have all of these different space telescopes that are optimized for asking different questions.
Right.
And so I think probably I may be missing something, but I think probably these interstellar asteroids like Oumuamua are not, Webb won't really add much to our knowledge of them compared to what other telescopes can do.
All right, so I'm going to keep it to 2 more questions, and I've already picked one of them, so you guys need to get your questions in. Crypto Man 5000 wants to know if you can talk about Rubin, similar to the Hubble-like telescope, if there's any time to talk about that.
You know, I'm not prepped to talk about Rubin. I only know it in the Vegas terms.
Okay.
I should have mentioned that. Well, no, I can tell a little bit about it. So Rubin is the Vera Rubin survey telescope on Earth, right? And it used to be called the LSST, the Large Synoptic Survey Telescope. And what's special about Rubin is it's going to look at basically the whole sky every night to see what changes. And so so unlike Hubble, which is a scalpel looking at, I'm going to look at this very specific thing in great detail. Rubin's going to look at everything and look for things that are weird, right? So it's going to find that Hubble doesn't tend to find things that, new objects that you didn't expect to be there, right? But Rubin will be like, what's out there that's behaving weirdly? Who's misbehaving today? That's the Rubin question, and so it's gonna, and the challenge of Rubin is that it is gonna get a large amount of data. I'm trying to think. I was going to say a less polite word, but it's it's going to get like petabytes a day or something ridiculous, right? It's going to be, and so the problem with Rubin is going to be not getting the data, but sieving the data for the stuff that's interesting. It's just going to be, we're going to be drowning in data from it, and so that's a good problem to have. And so I think it will make a lot of discoveries, and it will show that ground-based telescopes can still do competitive science.
Yeah.
Even
still
in the
got
era
it.
of Hubble and Webb, right? Now the challenge is we're going to lose the day. It's not going to be as good as we'd hoped because, of course, of our friends the Starlinks, which are a particular problem for Rubin. They're going to ruin some of the data from Rubin, but hopefully not most of it. So if we can see our way past the foreground of the satellite streaks, there's a lot of stuff out there in the universe that Rubin will be able to see.
A tree in the forest says, thanks for answering my question about exoplanets earlier. The answer kind of blew another fuse in my brain, though. Really enjoying this live stream. So I'm gonna, Marina keeps asking, will James Webb show us an image of Laniakea?
Laniakea, yeah, no. And the reason is Laniakea, I'm not sure I'm pronouncing it right either.
Can you tell us what that is? I don't know what that is.
Yeah. Laniakea is a supercluster of galaxies.
Okay.
And it's actually, we're kind of in it. Actually, I think it's a cluster of superclusters. It's a big structure in the local universe. That the universe is lumpy on all scales, right? And so there are parts of the universe that have more galaxies and parts that have less galaxies. And we're in a part of the universe that has more galaxies. And that big lump that we're part of is Laniakea. And we find it by mapping out millions and millions of galaxies and measuring their distances and motions, and sort of looking for patterns and realizing that, oh yeah, this group of galaxies is all kind of, connected and feeling each other's gravity. And that is, it covers, where are the galaxies in Laniakea on the sky? They're all over the sky, right, at different distances and stuff like that. And so you have to map the whole sky of galaxies all across the sky. And so Webb isn't the right tool for that. Webb is the scalpel that looks at a narrow piece. It might add some data. You might get from Webb some spectra that add, some more redshift data into the database. But it's going to be like 1% of the data that you then analyze to get the information about Laniakea. So it's you don't take a picture of Laniakea, you make a catalog of galaxies and like construct a model that then you have a picture on your computer that you've inferred what's there.
One last kind of comment. Michael in space says, Jonathan, tell them Pluto is a planet.
I can't do that. It's a dwarf planet. There's there are people who've made very strong arguments recently that the IAU decision about the definition of planets was a bad one, but I still feel like it's the, even though the technical arguments you can disagree with, the idea that we should teach people that there are 8 planets in the solar system and Pluto isn't one of them is a reasonable way of looking at the solar system. There are 8 large objects, and then there are 200 smaller objects that are still worlds. And Pluto is one, and Ceres is one, and Titan is one. But that I think if you're going to teach the elementary school kids the first cut understanding of the solar system, stopping at Neptune is a good place to stop, because I can teach the kids 8 names and I can't teach them 200 names.
Yeah.
Right. And so I think without gerrymandering, you can't include Pluto without including that other 200.
Well, I think we've started a Pluto debate in the comments, so I'm not gonna.
Yeah, no, this is one of these very touchy issues. Yeah, Pluto is the king of the dwarf planets instead of being the runt of the big planets.
Yes.
I think, but yeah, people are very attached to Pluto. I mean, Pluto is a great world to study, and I'll tell you my real answer is that I actually think planet isn't a very useful idea.
Oh.
Because it's so, even though people have argued that you can generalize the word, it's or let's say it has limited usefulness because it draws attention to the difference between planet and moon, right? A planet goes around the sun, a moon goes around the planet. And that's interesting for certain points of view. But mostly what we're interested in is this a big thing or a small thing? Is this a thing with an atmosphere or is it a small rock? And that includes a lot of things that we would normally call moons. Mm-hmm. And so I prefer to move away, at least in the typical discussions, from using the words planets and moons, and instead talk about worlds. And so a world is something that doesn't matter where it's orbiting. What matters is it big enough to be a place? You know, as opposed to, say, something I don't think is a world is Bennu, the asteroid that we got the sample from. It's a few miles across. That's a rock, a big rock. It's a mountain in space, but it's not a world. It's right. Not round. It's not, it doesn't have an atmosphere. You don't have to have an atmosphere, but it's that sort of distinction, right? And so I think it's better for people to focus on the worlds.
All right. That's a good answer.
And Pluto is a world.
Pluto is a world, a whole new world.
Yeah.
Yeah. Thank you so much to Jonathan McDowell for being on the Ellie in Space live stream today. I mean, seriously, great questions, everyone who's participated.
Yeah. Thanks for all the questions.
Yeah. Well, thanks for all the answers. And I guess your homework is to finish. Don't look up because I have more follow-up questions. I always have questions for you. So I really appreciate you taking time out of your Sunday and just, again, what a great accomplishment with James Webb.
Yeah.
Yeah.
That, the really hard part is over. No, the insanely hard part is over. Now we're just onto the really hard part.
Right.
Right.
I think we can handle.
Yeah, I hope so.
Well, hey,
we'll know in 6 months when we get the first pictures.
And I'll be talking to you then as well.
All right.
Enjoy your roast beef, and that's what you're having, right?
Yeah, I don't know. I might go for the sushi. I think it's a bit cold.
What is that sushi place called again?
Oh, Ebby.
Ebby
Sushi in Union Square in Somerville, Mass. Yes, highly recommended.
Shout out.
I'm not. I'm right now, because of Omicron, I'm staying in and getting ordering in.
Right. But still great food to have for takeout.
Oh yeah.
Well, enjoy that so much. And